section 8.3, we're going to learn another test for convergence and divergence for series. We are also going to learn another fancy series. All right, so our new test. Okay, we already have the geometric test, which has its own specific test for convergence and divergence. We have the telescoping, which does. But then we also learned the nth term test. Okay, well now we're going to learn the integral test. Okay, now this integral test is for convergence, and it's good for functions that you can integrate. I know that sounds kind of sarcastic. You can't use the integral test unless you know how to integrate it, but it's true. Now, when you're thinking about the integral test, I want you to think about anything we have ever integrated. So that means we could use substitutions. We can do integration by parts. We can do trigonometric substitution, partial fractions, inverse trig functions. Everything is open for us. So when we're using that integral test, like I said, you're going to use that for a function you can integrate. It needs to be positive, continuous, and decreasing for x greater than or equal to 1. Then we're going to look at that series. We're going to change it into an integral, and we're going to find where that integral is going. Okay? Either they both converge or they both diverge. So when I find that integral, if that converges, then I know my series converges. If it diverges, I know my series diverges. Now you can already see that looking at this limit or looking at this integral, we're going to have to do what we did in section 7.8, which is do the limit as some variable approaches positive infinity. So let's see if we can figure this out. So let's do a couple of tests. Now when I look at this, we're positive, we're decreasing, it's something I can integrate. So I'm going to rewrite this as the integral, going from 1 to infinity. I'm going to have my x over x squared plus 1. And put my little dx in there. Because my limit is infinity, I'm going to change it. I'm just going to put b. We could put m. We could put any letter we want. Although, remember, when I chose L, that wasn't a winner. So when I'm looking at this, when I integrate this, I'm going to use a u substitution. So my u is going to be x squared plus 1, which makes my du 2x dx. I don't have that 2, but I'm going to have it here in a minute. So I'm going to put the 2 in, counteract it with the 1/2, and I'm ready to go. I'm going to be finding the limit as b approaches infinity of 1/2, 1 to b, of du over u. So I've got a natural log. And remember, when you have that natural log, you're going to have to change it back into your x's before you sub in those numbers. Okay. So when I sub those in, limit as b approaches infinity of 1/2 natural log of b squared plus 1. Get that guy up there. Minus 1/2 of 1 squared plus 1. Whew, barely scraped that on there. Okay, so when I look at that, I'm going to have the limit as b approaches infinity of 1/2 natural log of b squared plus 1 minus 1/2 natural log of 2. I don't need the absolute values anymore. Well, when I put really big numbers in here and I square them and I add 1, I'm going to get a really big number. When I take the natural log of a really big number, this is going to infinity. So this diverges. Therefore, my series diverges. So we got to tell them what we found and what this means about the series. Okay? Let's do another one. Ooh, this one's a good refresher. Okay, we are proper, ready to go. So I'm going to change it into my integral here. Don't forget to rewrite your integral. Make sure you have your dx, whatever variable you choose. If you want to stick with ends, you can. I'm going to do the limit as that b approaches infinity of 1 over x squared plus 1. Now when I look at this, I don't have a u substitution. I have 1 over x squared plus 1 squared plus a square. I have arc tangent. So the limit as b approaches infinity of arctan wow, that handwriting's not getting any better, kids. Okay, and that is going to be x over a or u over a, so I've got just x. Putting the b in, putting the 1 in. I've got the limit as b approaches infinity of arctan, and remember, arctan is the same thing as inverse tangent of b minus tan inverse of 1. Now, when you're looking at inverse tangent, remember what we can put in is everything. Tangent's not picky. What we get for our answer, remember, we had to make this 1-to-1. So we could only get answers in between negative pi over 2 and positive pi over 2. Because we are headed towards positive infinity, remember what your inverse graph looks like there. Positive infinity, we're looking at that asymptote. Well, what angle in between negative pi over 2 and positive pi over 2 gives us an asymptote where my function's headed towards positive infinity? That would be pi over 2. That's why these are parentheses, is because those are asymptotes. Inverse tangent of 1, if it's positive 1, it's going to be a reference angle. In between 0 and pi over 2, it's got to be pi over 4. That's what's going to give us a tangent of 1. So that gives me a pi over 4 for an answer, which means I converge, which means my series converges. So a lot of things we have to remember. So let's learn a new series. We have our arithmetic, we have our geometric, we have our telescoping. Well, now we have p-series. Now you're going to like the p-series because just like your geometric series, it comes with its own convergence and divergence test. So if you know your geometric or p-series, you don't have to come up with one of those fancy tests, nth term or integral. You're going to use their specific test. And usually if they have a specific test, it's going to be easy. Now a p-series, you've got 1 over n to the p power, which means your base is the one that's going to be changing, not your power. So you've got 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p. Now, you've got a special name if p is 1. Okay, they call that a harmonic series. All the others just lumped into p series. Now, a p series is convergent if p is greater than 1. So if you have 1 over n to the second power, you are going to be divergent if p is in between 0 and 1, including 1. So just by this, automatically, you know that a harmonic series is divergent. Okay, so let's take a peek at it. Once again, this is lovely. You can tell it is a harmonic p-series. Okay, p is 1. Therefore, this guy is divergent. Here, p is equal to 2, which is greater than 1, so this converges. Okay? Love those tests. Now, this guy is not a p-series. It follows all the criteria for the integral test, so that's what we're going to do. We're going to be going from 2 to infinity. Doesn't matter what that number is. We're not falling for it. We've got 1 over n natural log of n. We're going to rewrite using our limits. So we have b to b to 2 of 1 over n natural log of n. Now whenever I see natural log, I was going to change that to x's, but I didn't, so I'm just going to leave it as n's. It doesn't matter, just make sure you have your dn there somewhere. All right, so when I'm looking at that, I know I have to do some kind of u substitution because I can't integrate natural logs. So u is going to be that natural log of n, which means du has to be 1 over n, and I have everything. So that's going to switch, still 2b, but that's going to be 1 over u du, or du over u, either way. Okay, we're going to have our natural log of the absolute value of u, which was natural log of n. Okay. And then we're going to put our b in and then our 2n. So limit as b approaches infinity of the natural log of b minus the natural log of 2. Okay. Well, the natural log of b here, when b gets really, really big, this is going to go to infinity. Infinity minus the natural log of 2 is still infinity, which means we diverge, which means our series diverges. And we write it out. Okay. Alrighty, I will see you back in class.